the kind of the goal of our language, and I'm going to talk about a bunch of different applications of this, but I kind of have to show you the basic technology first, is to be able to compute about anything. So I just took a picture there, and now I could say, let me compute something based on that picture. So let's say I make edge detection of that picture, or I could say, and let's say here, I could start saying, I don't know, let's try something like image identify that picture, see what it can. So this is now doing, okay, so great, it says it's a person, good. That's a good sign. Actually, let's ask it what it, if it wasn't, if it didn't think it was a person, what are the probabilities that it might be something different? Let's see what kind of crazy things. Okay, so it's pretty certain it's a person, it's even more certain it's a vertebrate, etc., etc., etc. So that's good. So this is just a standard feature of Wolfram language, being able to, this is kind of doing some basic machine learning kinds of things. Now, as we start thinking about, okay, imagine we were writing a computational contract about things that should happen in the world. We might actually need the contract to say, if the thing that walks up to the door is a cat, let it in. Or if the self-driving car sees a bear on the road, do this. If it sees a horse on the road, do something different. Actually, we can try just for fun. We can just see what happens if I. Okay, great. So, but what I'm doing here is I'm using the fact that Wolfram language knows a lot of stuff about the world. So I just said horse. Okay, let's try and get an image of a horse. Okay, let's see whether the image identifier says that that's actually a horse. Oh no, just try it. A rowan. What is a rowan? Anybody know what a rowan is? Let's see. Word definition. Okay. That was pretty cool, actually. I don't know if it's correct, but it has so in any case, kind of just to sort of set more of the kind of outline here, the goal is have the language know a lot of stuff about the world, and be able to compute things about the world. So for example, let's say we want to know, let's ask about state capitals in the US. Going to understand that? So what that's doing is, so first of all, I'm using natural language as a way to start interacting with our computational language, but then what that turns into is something which is a completely computable thing. So if I say, give me a list of those entities, okay, there would be the list of state capitals in the US. Probably if I say geolist plot of that, it'll make me a plot of where those state capitals are. Maybe I can, okay, let's say I want to compute something about these. Let's say I want to visit all the state capitals, and I'm going to take a plane, and I want to take the minimum distance between all those state capitals. So maybe I could now say, what's the geoposition of the state capitals? They were on line 12. So we'll ask for those geopositions, and now we'll say, find shortest tour. And this should give us those, it says there's a 16,000-mile tour that visits all those state capitals. So if we take the state capitals and we say that, this should give us the state capitals in the order that corresponds to the shortest tour. So let's say I say, just display that. Okay, there we go. So that's now showing us the shortest tour visiting all the state capitals in the US. Now, I think it's pretty neat that we can, all of this is built-in knowledge in our language. And kind of the idea, in typical computer languages, people say, well, let's just build a small language inside that can describe, can be able to tell the computer in kind of its terms what operations it should do, whether that language is, C or Java, Python or Ethereum virtual machine language, any of these kinds of things. You're ultimately sort of pandering to the details of what a computer does when you specify things in the language. What we're trying to do in Wolfram Language is to rather kind of encode the knowledge, methods, models, algorithms, and so on that we as a civilization have developed and make them all sort of immediately accessible in the language. And I suppose the bigger picture is when we think about computation is a very powerful tool for doing things. I mean, one of the things that we can realize is for pretty much every field of human endeavor, call it X, there's either now a computational X or there will be a computational X, and that'll typically be the future of the field, whether it's computational archaeology or computational zoology, any of these kinds of things. The kind of computation is the paradigm of our time, and it's very powerful. And in a sense, there's a lot that can be done with computation. Is you can do a lot of things with computation. The question then is, how do we humans tell computers what we want them to do? And it's sort of an interesting progression of how we express ourselves. I mean, back a long time ago, there was only spoken language, then we got written language. Then about 300 or 400 years ago, we got things like mathematical notation. Before 300 or 400 years ago, when people wanted to specify mathematical kinds of things, they would write them out in words, and mathematics didn't progress that fast at that time because it was kind of hard to untangle what was going on with words. Well, one of the things that we're trying to do now is to have a computational language which can express computational ideas, computational thinking, in a way that both computers can understand and we humans can understand. So one of the things I find most important about our language is it's a way of expressing computationally formulatable thoughts. Human language provides us with a variety of ways to express ourselves. Mathematical notation provides a way to express ourselves. Our computational language provides a way to express ourselves. And that's super important when you start thinking about computational contracts, for example, because computational contracts are an attempt to make sort of a precise specification of things that should happen in the world. So we have to kind of be able to express ourselves computationally and talk about things in the world. So, it's interesting to see, I don't know, we could make what could we do? We could make something like, just get a sense of what this language looks like. I mean, we could say, give me a list of words. Okay, let's take the first letter from each of those words. Let's list of words in English, and then let's make a word cloud of the first letter of all those words in English. And so kind of what's important about this is it's pretty easy to read what's going on here. This is not something which is sort of pandering to the low-level operations of the computer. This is something which is intended to be something that we humans can actually understand and think in terms of. And it's something that's it's a very important thing in terms of sort of being able to find a way to formulate our thoughts computationally, that we try to make a language that can express those thoughts so that we can sort of make concrete the things we're thinking about. Okay, so we're trying to represent all sorts of different kinds of things in the world, all sorts of different kinds of data about the world. I don't know, we could take, let's do something here. Let's take let us live slightly dangerously. Let's get 20 random movies, okay? And now let's say something like, let's actually, I'm going to get a little bit more. Let's get 30 random movies. And let's say whether let's try and get the movie posters for those 30 random movies. Okay, lots of them aren't available. Let's get rid of the ones that aren't available. So this is not too many there, and we could do something like, we could say, given these movie posters, we could say, show us a 3D chromaticity plot showing us, where in color space the colors in those movie posters are. Or more interestingly, we could do something like, we could say something like, plot those movie posters in some kind of feature space. I don't think there'll be enough that this will look very interesting. But if we had enough, we'd probably see that the horror movies were off in one corner because they have kind of dark posters and things like this. Why is that relevant to things like computational contracts? That's sort of the beginning of understanding when you say, I'm going to make a movie and it's not going to be a horror movie, and the contract says it's not going to be a horror movie. It's like, what are the definitions of what it means to be a horror movie and so on, and that's where you have to start digging into these kinds of things. I mean, it's also relevant when you start thinking about, well, let's, we could say, let me maybe just talk a little bit about what computational contracts might look like. So, for example, one contract we might write is something about, I don't know, if we might make some weather insurance. We might say, if it rains tomorrow in Austin, then pay some amount of money. We can also, so let's see what would happen. Let's say we want to say, what's the, let's ask for Austin, Texas, let's say, what was the air temperature in Austin? Let's just ask for it for the last month, for instance. So this is going to show us, this is, again, just data that we can get. Let's see what it looks like. So that's showing us, okay, so this already shows us a bunch of interesting issues. So this is the air temperature data measured in Austin for the last month. Okay, so let's say we're writing a computational contract that's about, if it is warmer than such and such a temperature, then then if you didn't show up for your, canoeing expedition or something, you lose the money or whatever else it is. Okay, but we already see something, an issue here. When we actually write that contract, there'll be a simple thing that just says, if air temperature data is greater than 70 degrees, then do this. But whoops, there's missing data there. Now, why is that data missing? Who knows? The weather station, the nearest weather station to the center of Austin happens to not have that data. There's nothing much we can do about that. It's just something that didn't happen to be delivered. So when you start thinking about writing that contract, you realize that you're going to have other provisions in this contract. Like you might say, well, it's not just enough to know what the temperature in Austin was. If the temperature in Austin is missing, use the temperature in 3 nearby cities as a proxy for that. And you start realizing that as you start trying to formulate what's in a computational contract, you start to have a bit more complexity there. And that's where you have to, like a typical legal contract, you'll end up with some very straightforward pieces, and then you'll end up with all kinds of complicated stuff about what happens if this happens or that happens or whatever. One thing about the world, and one thing people want to write contracts about, is things about blockchain itself. And I might say that when I talk about computational contracts, people talk a lot about things like smart contracts on blockchains like Ethereum and so on. And what they mean by that is typically code that can be written in Solidity or whatever that runs in the EVM, that is code that relates to things that the EVM can know about, which is basically stuff that's happening on the blockchain. Now the problem is that a lot of things that we actually care about writing contracts about are not things that happen purely on the blockchain. They're not transfers that happen on the blockchain. They're not things known directly to the blockchain. They're things that require some knowledge of the outside world. They require what people sometimes call an oracle. It's a really terrible name because oracles in the classical tradition were things that foretold the future, which is exactly what this is not doing. This is, it's something where one is really, it's a thing which is a source of computational facts. That's what one needs. One needs facts about the world, what actually happened in the world, because that's what will determine which way one's contract will go. Well, actually, it turns out right now that if you want to get sort of a source of facts about the world, you want to get a source of facts about the world that a computer can deal with, computable facts about the world, for better or worse, the single broad-scale source of those facts is the API that we have for Wolfram Alpha. So Wolfram Alpha is this computational knowledge engine that we built 9 years ago now, which gets used at least by most students in the US, for example, use it. Maybe some of you here. Who here has used Wolfram Alpha, actually? Okay, that's interesting. All right. In a slightly younger demographic, it would be basically 100%. I think actually Wolfram Alpha nowadays powers the computational knowledge system of Siri and also now of Alexa. it's the thing that is generating kind of computational facts about the world. And when people have built kind of oracle systems for blockchain that know facts about the world, they basically all use our Wolfram Alpha API. This is kind of the thing that one needs to kind of go beyond the pure sort of about the blockchain itself smart contract world is a source of computational facts. And as I say, the Wolfram Alpha API is a source of public facts about the world. So we know, what's the price of gold? Did it rain in Austin? What was the box office result from this movie? Who won this election? All these kinds of public facts about the world. I think one class of facts that we also know are facts about blockchain itself. So if I say, let's say, for example, I don't know, blockchain, block data, let's just do this. Let's say for Bitcoin. So this should tell us, I hope, yes, there we go. So that's the most recent block that was mined on the Bitcoin blockchain. And so this again becomes just computable data for our system. And so we can take, we can take some random transaction here, we can start looking at that transaction, we can do things from that, we can do something a bit more, oh gosh, there's lots of these. Wow, what a mess. Okay, we can, that's why it took a moment to bring that in. But we can, start making graphs. I don't know, let's say we start making a graph of how these transactions relate to each other. I'll probably make the actual graph here, but I can simulate a graph of how the transactions relate. I just make, a random graph here, and I can start computing things about that graph of transactions. And it's actually quite, we've been progressively getting better and better kind of ability to do analytics on blockchains, and it's quite interesting to see what one can see there. Like for example, let me do this. Let's say blockchain token data. Let us try something like let's try. Let's see if this works. Let's see. Yeah, there we go. Okay, so let's try. Okay, so this is asking about ERC-721 tokens assumed to be on Ethereum, and this is going to hopefully show us a data set of so this has various pieces of information. So let's see, what should we look? Let's say a count of let's look at the holders count, the number of holders. So let's say we want to say that, and we want to ask for all. And we want to say let's say the name and the holders count. So this is now asking, hopefully, okay. And then let's say, that's not quite what I wanted it to do. Let's see. All right, I actually have to write some code here, gosh. All right, let's do this. Let's say the name and the holders count. Always good to see real code being written. All right, there we go. And now let's say, actually what I want to do here is I want to say, given that name, I want to say that's the amount of, that's that. So here I can do that, and hopefully I can say, make a word cloud here. I want to do it the other way around. All right, let's try this. Let us see whether that can make a word cloud here. Okay, so it's happening. There we go. All right. So that's interesting. So this is by holders count. This is the number of ERC-721 tokens. This is a word cloud of which tokens have the most holders. I actually have never heard of this one, but we could drill in and look at more details of that. But so this is the kind of thing that we can easily sort of know about the blockchain world from our language. Now, I was mentioning kind of sources of facts about the world And there are kind of public facts about the world, there are facts about blockchain. Another class of facts are facts that come from like sensors, IoT sensors, for example, measuring things in the world. And that's sort of an interesting class of facts. I mean, in our language, we can easily, we have this mechanism of data drop, which is a way of getting, accumulating data from, so these are particular data drops that I have. I don't know, this is one for a Wi-Fi signal in my house, 643,000 samples of that. But I could take one of these things and I could say I could ask it to show me the results that it has from here. But anyway, I'm getting data from sensors in the outside world. And that's another source of data that's relevant for computational contracts. There are a couple of issues with sensor data. One basic question is the sensor data correct? Like, for example, let's say somebody has a contract that says if they walk 10,000 steps in a day, then their company will give them an extra, healthcare, bonus or some such other thing. And then the question is, did they actually walk that 10,000 steps? Or did they get their pedometer and put it on some arm that was just going back and forth 10,000 times that day? And so there's sort of a question of how do you validate data that is coming from, in some cases, just one sensor somewhere in the world. And I think there are two basic approaches to that. One is that, this is going to take too long to load over the network, but one approach to that is to use machine learning and use anomaly detection in machine learning to try and figure out, given that we have seen this pattern of data, is this thing that we are now being presented an anomaly or not? That's kind of step one. That's kind of a black box way of seeing what's true about what the data that you receive in the world. The other thing is to actually have a model of what's going on in the world. And for example, in our language, we have kind of models of many kinds of devices and so on in the world, and we can start to compute, is this a reasonable set of data to have been generated for this particular IoT device? Well, so in any case, the basic thing here is we're creating computational contracts, we're writing them in a computational language that both the computers can understand and we as humans can understand. So, what does the lawyer of the future do? The lawyer of the future probably doesn't write legalese. The lawyer of the future probably writes computational contracts. And just like with standard legal contracts, they'll boilerplate, they'll be essentially chunks of computational language that get reused because they're a good thing to describe such and such a kind of piece of a contract. And then these computational contracts will contain some things that are precise. Some things like, if the temperature is greater than 60 degrees and so on. They'll contain some things that are a bit vaguer, that will say things like, both parties agree that they're delivering fruit that's in good condition. What does it mean to be in good condition? Well, it means that the image identifier, when it takes a picture of the fruit, will conclude that's been trained on fruit that's in good condition, fruit that's in bad condition. Both parties will agree that if the image identifier says that the fruit is in good condition, then it's considered to be in good condition for purposes of the contract. But so what will then happen is when we'll have all of these computational contracts that represent things about what one wants to have happen in the world. Sometimes those contracts will say at the end of it, and pay somebody some amount of cryptocurrency. Often they might say, just pay somebody something in fiat currency, or they might say, make this thing happen in the world, actuate this particular kind of thing in the world. But this is, that's kind of the structure of what will happen. I think that, some people say, well, if you're computerizing all of this contract stuff and all this, you're making all this kind of computational law, doesn't that mean there won't be any need for lawyers and so on? Doesn't that mean? Well, I think it's kind of like the paperless office situation, that as soon as it becomes easier to make computational contracts, there will be a lot more contracts in the world, because on any given, the cost of making a contract and executing that contract will be vastly lower. So one of the things that then happens is that this kind of usually in computing right now, we're in a situation where you're asking your computer, go do something for me, the computer does something, maybe it does something. What will happen in this sort of world where there's a whole network of computational contracts is that there'll be a lot of autonomous AI, autonomous execution of these contracts that will just happen in the world depending on things that occur in real life, so to speak. So one of the things about computational facts that's sort of interesting, a little bit scary to somebody like me, who's a provider of computational facts, is that there'll be this big network of computational contracts, and when a computational fact emerges in the world, it's like a giant domino effect. The computational fact, somebody wins this particular election or something, and then there's this giant chain of computational contracts that will trigger as a result of that computational fact. So there are all kinds of issues about how do you do your best possible job at making sure that the fact is correct in some sense of correct. I think my basic point of view is we can make it so that the provider of facts is not crooked. We can't necessarily make sure the facts are correct, but we can at least make sure that they are not, that there's nothing dishonest about the way they're producing, talk about how that's actually can be achieved. So one of the things, as we start thinking about this kind of world where what's happening is that we have these computational contracts that define what's going to happen, kind of thinking about what some of the important kinds of contracts that we have to write are. I think one that's perhaps interesting is when we think about AIs that do things in the world. So, AIs that drive cars, AIs that manage the money supply for central banks, things like this. One question is, what do we tell the AIs we want them to do? And people, I mentioned kind of the progression of automation in the world. I think the thing we realize is that there's one thing that we can never automate, which is the what do we actually want to have happen in the world question. We can't automate. The question of what we are trying to do is a question that is necessarily something that we humans have to decide. But the issue is, how do we tell the AIs what we want them to do? So there's a whole network of AIs that learn all kinds of things in the world. What do we tell them to do? We might say, well, let's just use, Asimov's 3 laws of robotics. That's not going to work very well. It doesn't get very far to say, and then people might say, well, the thing we want to do is there's this one golden rule that AIs have to follow, and then everything will work out great. So an interesting question, our experience from human legal systems is that that's not the way it works. Human legal systems get pretty complicated. And so I think what we have to realize is that when we're dealing with kind of a very important computational contract for us, which is the sort of global constitution of what the AIs should do, we have to expect that that's not going to be some simple, 3-line contract that just says, okay, AIs, be nice to humans, whatever that means. Because we have to kind of say, and we're sort of thrown into a lot of the classic issues of political philosophy. If the AI controls the central bank and can decide, what's it aiming for? Is it aiming to, make the most people on average happier? Is it aiming to make the least happy people less unhappy? What is it aiming to do? These are old questions of political philosophy, but now we have to think about what's the actual code going to look like, what's it going to actually say to do. And what we realize is the AIs may be perfectly capable of doing better than economists have done at managing money supplies or whatever else, but we still have to tell them what do we want to have happen. And for that we have to create a computational contract that describes what we want to have happen. And I think what inevitably will happen with those contracts is they may start fairly simple, but like legal codes for humans, they'll end up getting pretty complicated. Is that because we're kind of stupid about it, or is that for some other reason? I think the thing to realize is there's kind of a necessary feature of computation that as soon as you have a system where the computations that are going on kind of aren't trivial, there will be bugs and unexpected consequences. That is, you say, I'm trying to make a system, I'm trying to make a set of rules that will guarantee that the world will work in this way, that the AIs will always be nice to humans, for example. Well, it turns out that that's not something you think you've got it, but then there'll be some kind of chain of events that will cause you to get to some unintended place that you won't have covered, so you have to patch that, and then you have to keep on doing that. And it's a kind of fundamental fact, actually. It follows basically from Gödel's theorem, result in mathematical logic, that you will never get a computational system that is such that you can always patch, that there'll be a finite number of patches that will always achieve kind of a thing that you want. And so that's an inevitable feature that of kind of a computational contract-based world, is that you'll always have this sort of whole collection of different sort of pieces that have to be added to the code of laws. But by the way, when you have computational contracts, there are all sorts of cool things you can do that you don't get to do with ordinary contracts. For example, you can start running automated theorem proving software to try and prove what will happen with these contracts. Now, the bad news about automated theorem proving is that, let's see if we can do an example here. Let's see. Something. Okay, so this is a little axiom system. You can think of this as a very simple sort of code of laws, a constraint. This happens to be the simplest axiom system for Boolean algebra. So we could take that axiom system and we could say, find an equational proof. So we're trying to, we could think of this as being trying to prove some property of prove that something happens in some way in, let's see, where can we go here? Let's say this one. Prove that something happens according to some set of rules. So here we can say, actually, I'll tell you what, let me do this. I'm going to try to prove that in this system that P dot Q equals Q dot P. Okay, so that's something rather trivial sounding, but let's see. Let me ask the system to try and make me a proof of that fact given that axiom system. So it's going to grind away for a while. This proof has 102 steps. So let's try to say, let's just ask, what does that proof look like? Okay, well, so here's the proof. And we can go and, it's got a lot of steps. We can go and look at each step. These are intermediate stages in the proof. If we wanted to, we could say, let's say, we could just make sort of the network of what the structure of that proof is. Okay, that's the structure of the proof. Okay, so this is really pretty hard to understand. And yes, it's pretty hard to understand. And actually, this is a necessary feature, again, of this sort of computational world, that you end up with things that are true, but where, although our computer can verify this is absolutely true, we can go through and check it's true. Can we as humans understand why it's true? Absolutely not. I mean, I did this proof originally by computer 20 years ago. Nobody has really understood, including me, sort of why it's true. We can't tell a kind of human story about why it's true. We can verify that, yes, formally, technically, by each step it's true, but we don't get to tell kind of a human story about what happened. And that's one feature of kind of the AI-based world, is that things, you compute things, but you don't necessarily get to be able to tell kind of a human story about why things turn out the way they turn out. I mean, in a sense, when we tell a human story about why things turn out the way they turn out, what we're doing is we're using, for example, words and languages to describe what happens, and the way that language evolves, for example, is that we only invent words for particular kinds of things. Like, for example, on blockchain, there are probably phenomena that happen on blockchains that are like, a blockchain tornado or something. That's some weird particular feature of the graph of transactions on a blockchain. But until we've kind of internalized that that's a thing, that that's an important thing, we don't have a word for it. And so we don't get to kind of tell a human understandable story about what's going on. That's something that gradually emerges, and for example, in an area like mathematics, it's been emerging for a couple of thousand years, and there have been more and more layers of kind of description and abstraction. So that's one feature of computational contracts. The good news is you can imagine doing automated verification of aspects of those contracts, check it doesn't do this, and so on. The bad news is you won't necessarily understand the things that are coming out. But there are all kinds of other things you can do with computational contracts. For example, you can simulate different kinds of things in the world. You can say, if this is if this is the contract about how things work, let me throw in a million different cases of what could happen in the world. A distribution of, what the weather was like, a distribution of, what the stock prices were like, and so on. Let me kind of quant it and figure out, given this contract, what are the likely outcomes in the world. Okay, so in any case, I wanted to the main takeaway, I suppose, from all of this is that we want to find a way to we have this opportunity that kind of blockchain has revealed that for making the world work through computational contracts. Now, right now, there are limited areas of the world, like options contracts for stocks, things like this, which are effectively computational contracts already. But it's a very limited corner of all possible contracts in the world. And as computational contracts become more widespread, lots of kinds of interesting things happen. I think that the way I see it, if one's looking at cryptocurrency, for example, to support a currency in a stable way, you need a lot of economic activity. I think the source of economic activity that can support cryptocurrencies potentially is computational contracts. And one day, there'll be trillions of dollars that flow through computational contracts. That hasn't happened yet, but it's something that we can plainly see is going to happen. Whether it will happen fast enough to kind of keep the value of things like cryptocurrencies today, I don't know, but that's kind of the trend of how things are going. And I think the thing that I want to kind of emphasize is when you think about making a computational contract, you have to think about how you express that computational contract. You need kind of a computational language understandable to humans and executable automatically by machines. By the way, this idea of computational contracts, you might think, oh, there's a very newfangled idea of the 2010s or whatever. Quite to the contrary. The idea of computational contracts actually dates back to the 1600s. I mean, people like Leibniz, his original motivation for lots of what he did was to kind of, in fact, his PhD thesis was about deciding legal cases using logic. And so his idea was, let's make a mechanical system, essentially a computer, that can do legal stuff and can decide and can create legal contracts and so on. Unfortunately, and it's a lesson to people like me who like to do kind of large-scale technology and science projects, it's a lesson in the don't be 300 years too early kind of story, because back in the 1680s, it was pretty tough Leibniz tried to do a bunch of things. He would have built Wolfram Alpha if he'd had the technology. But as it was, what he built was, he got as far as building a 4-function mechanical calculator out of brass. That took him 30 years to get to work, actually. And he went around to dukes and so on, convincing them to try and collect knowledge in books and libraries and so on. But clearly, 300 years too early. What's kind of exciting now, but he had this idea of making he called it a characteristica universalis, a philosophical language that could kind of symbolically represent everything in the world. And that idea of, can we make a language that represents in some precise computational symbolic way things in the world, that idea has sort of languished for about 300 years. I think I've been interested in it for a while. Now with computational contracts, we finally have a reason to actually finish that project. And we've obviously got a fair distance with Wolfram Language now. We've built a way of expressing things about the world and so on. I think it's actually possible to finish that job and kind of make a complete symbolic discourse language that can kind of represent kind of everyday things that we talk about in the world. And kind of, that's an interesting conceptual thing to do. It's also an interesting practical thing to do because it means we get to write our currently legalese contracts in a precise computational form, which means that they can be automatically, we can do all sorts of processing and analysis on them, but they can automatically be executed by machines. And then in the sort of blockchain world, what we end up with is this kind of autonomous computation where there are a bunch of contracts that sort of just exist in the world and get executed depending on what happens in the world. So that's kind of my view of how things will evolve. And I think the important thing for us humans is, make sure we can actually communicate in computational language, where we communicate just fine in natural language. Some people communicate in mathematical language. It's something where we're now in a position to teach the next generation or this generation kind of how to communicate in computational language, how to express themselves in a way that is kind of computationally precise. All right, I will stop there, and I'm really happy to have questions, comments, discussion. Thank you. Please.
So
looks like there's
it's going to take me a while to get to the mic, so I'll
okay.
just yell out.
I can hear you.
So just as we're debating the liability of automatic driving cars, what is the future of malpractice?
Okay. Let's see if I can unpack that question. So the question was, what's the future of malpractice? So I guess there are different levels of that. So the question is, a human, who is responsible when the self-driving car goes off track? And is it the, let's take another example. Let's take the example of autonomous weapons, okay, which is a case where, so one question there would be, what do we want the autonomous weapons to do? They've got some rules of engagement, they're represented by a computational contract. How do we decide what those should be? And so there's no abstract way to decide that. We as a society or a country or whatever have to decide this is what we want to have happen. And once that computational contract is written, and however it's written, however that, whatever system of human governance we use to write that, once that's written, then the actual execution of that contract, hopefully, we will get, there are a couple of different issues. Is the contract wrong? Was there a bug in the execution? Okay? I think those are two different things. So was the contract wrong? It's like, well, this is the contract. Everybody can see it. If you don't like the contract, well, that's a different thing to complain about. Was there a bug in the execution of the contract? That's a complicated issue. I mean, what's happened in the software industry, when I entered the software industry a long time ago, I actually thought the software industry would be destroyed by essentially malpractice suits. But I thought that it might be the case that that every time there was a bug in a piece of software, there'd be just piles of litigation. Okay? Now, it turns out people got used to the idea that software has bugs, which is a good thing because it's theoretically necessary. It's not something that is just because we're stupid, software has bugs. It is always the case that there will be unintended, unexpected features of a computational system. And so I think people, having gotten used to that, it's kind of, you don't even really need the disclaimer that says, well, this software might have bugs, because everybody kind of knows it might have bugs. So I think that's the best I can say. So there's one other point I might make, which is this whole issue of unintended consequences, and the question of whether you can expect to foresee every possible unintended consequence. The answer is no. The answer is we can theoretically show that you can't foresee every unintended consequence. So what does that mean for how we write our laws about malpractice? It's complicated, I don't know. Please.
Yeah, thanks for coming and sharing your insights at South by. We all appreciate that, of course. And do you think, in the recent news that the utopia we all thought we had in blockchain, even though it's mostly the exchanges, but now the utopia that it was secure, blah, 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 has all been hacked, out there. Is AI going to help us really solve that, other than we're elected, reckless people with their passwords, IDs, blah, blah, blah? You can't do much if somebody's reckless, but as far as the system itself being secure, is AI going to help us?
Security is a complicated issue. What do you mean by something being secure? I mean, so what you end up with, you're back to computational contracts, because security is essentially a contract about what should happen. I mean, in other words, fair enough. So that's a piece of your contract that says, I don't want to lose my holdings. Okay, what happens if let's give a crazy example. Let's say you have given your holdings to a company, and the company is in a jurisdiction which stops existing. You know, it's in a country that, you know, it's a company registered in a country that doesn't exist anymore. I just made that up, but you know, then what actually happens, right? So the whole point is to say, I don't want to lose my holdings. It's like saying to the AIs, be nice to humans. It gets a bit more complicated. And the way to kind of set it up, I think, is to think about all these things as computational contracts, and to imagine that the way you're specifying what you want to have happen is to write it as a computational contract, a computational language that you can understand and that the system can execute. Now the question is, are there bugs effectively in the code that will cause that computational contract to not be correctly executed? Well, this is a complicated issue because, as I was mentioning, bugs are inevitable. Bugs are not just a matter of human stupidity, so to speak. They're a matter of a necessary feature of computational systems. I mean, one of my sort of favorite examples, I've studied a lot, this question about sort of what programs out in the wild actually do. So for instance, if I were to look at a program that just determines, you know, it's just based on updating a line of cells with black and white squares, I could just say, let's see, something like this. I could just say, oops, I did that wrong. You know, that's what that particular program does. You say, okay, fine, that's pretty straightforward. I can foresee what that program is going to do. Okay? Let me change that program just a tiny bit. Okay, now let me run it again. And now the question is, what's that program going to do? We don't know. We can run the program, we can see what happens, but there's a phenomenon, a science phenomenon I call computational irreducibility, that basically says we can't know what that program is going to do much faster than just running it and seeing what happens. And that's an inevitable feature of computational systems, and that's something when we say, let's make sure that there's computer security that's okay, that's the kind of thing we run into. So as a practical matter in computer security, one of the issues is that every time we have a sophisticated computational system, whether it's a router, whether it's some other kind of thing, anytime we have some system that is capable of being a universal computer, we have a problem with this kind of thing. Because once the system is capable of being a universal computer, it can kind of escape to show any computational behavior. And constraining it is essentially arbitrarily difficult. And we have the same issue as constraining the AIs not to do anything we don't want them to do. It's kind of like putting a bunch of patches of computational contracts. So it's complicated. I don't think there's a perfect answer. I think that our ability to kind of surveil the world or the blockchain world and see are there anomalies happening, sure, we can do some of that. I mean, there's nice things we could imagine doing with modern machine learning to say, oh, let's make sure nothing happens that isn't something that we're used to having happen before. By the way, just as a sort of thought experiment, one of the issues is, let's say we make a constitution for the AIs, and we say, this is how we want AIs to behave. And AIs control the world. And now we go 100 years in the future, and we put this contract in place now in 2019 or something. This is how AIs should work. Well, 100 years from now, the AIs who are in charge, so to speak, are like, yeah, we're following the contract. It's exactly what you told us to do. What's the mechanism by which you can change the constitution, so to speak? You know, in human constitutions, people usually we'll have a supermajority in a democracy, or we'll have some, you know, sort of ultimate ruler who will decide, or actually, I think, I was trying to understand some of the Soviet-type constitutions where I think it's like there's such an infinite chain of bureaucracy that you actually can't tell what will happen, so to speak. But
the unknown unknowns.
Yes. But anyway, so there are issues like this. Anyway, please.
First off, thanks so much. That was truly fascinating. But when you're saying that we need to be able to describe in language what these computational contracts are doing and to interact with them, what happens when the AI creates their own computational language and we can't interact with that anymore? What happens then?
Well, okay, so that is a routine thing that has already happened. Okay, so if we look at a typical, I don't know, the insides of an image identifier, okay, the system will have made a bunch of distinctions. You know, in order to identify an image, it's basically saying, in a simple-minded way, it's saying, is the thing round, is it square, is it green, is it blue, etc. Those are distinctions that we understand. But in fact, when we've trained an image identifier, it is coming up with really very successful distinctions, but they're not distinctions for which we have words. And so when we say what's going on inside this thing, we don't get to tell an easy story about what's happening. I mean, this idea that one can tell a story about how things work is kind of an illusion, because, for example, in the natural world, when we see, I don't know, the behavior of the weather or something like this, maybe we can get to tell a story. There's a low pressure zone here that causes this, that causes that, and so on. But in fact, the weather is governed by a bunch of differential equations and things like this, and they just do what they do, and we don't necessarily have an easy human story that we can tell about them. We are spoiled for the following reason, which is that we invent certain things, we invent certain abstractions and so on, that we then build our world around. So for example, once we have the idea of rooms in houses, then everything is rooms in houses and we get to describe that, or roads or something like this. We get to describe things in terms of that. So it looks to us like things are understandable because we've built our environment to be an environment that is understandable because we've built it using concepts that we've already constructed. But the natural world, for example, isn't under that constraint. The natural world doesn't have any requirement to be understandable. And in the sort of computational universe of possible programs and so on, the vast majority are not understandable. It turns out the ones we typically use in modern and current software engineering, those ones we specifically construct to be understandable to us. But the ones that are the most efficient aren't. By the way, I might mention one thing about these things like cellular automata, and this is a thing called the cellular automaton, and this phenomenon of computational irreducibility. It's just a funny little anecdote. I mean, I invented this idea of computational irreducibility in the early 1980s. And it's sort of this idea that you can't compute faster than by just watching the running of the steps. And I was, what's the significance of computational irreducibility? It has a bunch of philosophical consequences, it has a bunch of consequences about how you do simulations and so on. But I had never foreseen that this idea would be used for proof of work for blockchains. I mean, the fact that computational irreducibility can be a thing of value on its own as a way to do proof of work was sort of a bizarre, unintended thing that came out of that idea. So it's just kind of it's some sort of, for me, as a when you think about basic science, you think, what are the consequences of basic science? That was for me a completely unexpected consequence of basic science. Please.
Excellent talk, Dr. Wolfram. I really enjoyed it. It occurs to me that we are not too far away from self-creating, self-organizing, and self-propagating blockchain and blockchain networks. Any comments on that? Any thoughts?
I mean, I think that this whole question, actually, I don't think I fully responded to this question about what happens when the AIs write their own, write their own code, so to speak. That is sort of happening all the time. I mean, that's what, when we train neural nets, that's effectively what's happening. Now, this question of whether, I think in a world where there are sort of a network of computational contracts and so on, yes, this will exactly happen. There will be things that we can, there'll be essentially code that is generated by virtue of those computational contracts. The contracts may even specify code should be produced to do this. And yes, it will get, I mean, what we're building is a sort of artificial natural world. That is, we're building something which has computation going on just like computation goes on in the natural world. We happen to be the originators of this. But it is not something where we will be able to know what's, all the things that are going on. I mean, it's the same thing in general that's happening with AI, is that we are the originators of what happens, but in the end, the AIs get to do stuff like this, which is stuff that is, it follows definite rules, but it isn't something where we can just say, oh, we as humans understand everything about what's going on here.
So it seems like we are creating a natural world that we don't understand, or will not understand.
Yeah, I mean, that's the feature of the natural world as it is that we don't, the fact is, okay, so to say this a little bit more precisely, this phenomenon of computational irreducibility is a consequence of a thing I call principle of computational equivalence. So in the sort of history of people making computers and things like that, it could have been the case that every different operation you wanted to do, like in Leibniz's time, he had no idea that there would be universal computers. He thought he was building an adding machine, he was building a multiplying machine, they were different pieces of, different brass objects, so to speak. But then in the 1930s, with Turing machines and so on, it became clear that it was possible to have universal computers, where you could have a single box, and just by feeding it in different software, different programs, you could get it to do any computation. Well, there's then the question that arose was, if you just take some random program that you get, you just pick it at random, some simple thing based on black and white squares, what kinds of computations will that do? Will that typically do, if it's a simple program, will it just do simple computations or not? So this principle of computational equivalence thing of mine is basically the statement that above a very low threshold, essentially all programs will be equivalent in the sophistication of computations that they can do. So they're all kind of max out the level of computational sophistication that can be achieved. Okay, so one example of a computational system is our brains and our computers. So when we look at a pattern like this, we can ask ourselves, are we smarter than this thing? So in other words, it's doing its computation, but we've got our brains, and can we jump ahead because we are more computationally sophisticated? The point of this principle of computational equivalence is no, we can't. We are equivalent in terms of computational sophistication to a system like this, and that's why we have this phenomenon of computational reducibility and so on.
Thank you.
Yeah.
Thanks so much for your insights. What are some cutting-edge AI research projects that you're working on that you can elaborate about?
What are the things I'm working on that I can talk about? Gosh, there are too many things. You know what, should we be going on for hours? We just brought out a new version of our, well, actually it isn't out yet. We will be bringing out in the next few weeks a new version of our language, version 12. And we have an annual technology conference, and I was talking about what's coming in version 12, and I will admit that I went on for 3.5 hours talking about that. So you don't want to get me started with all the things that we're working on. But I would say this in terms of the types of things we're discussing. Some of this symbolic discourse language, as I call it, this way of representing, turning everything in the world into something that can be represented symbolically. That's kind of a big story of what I'm trying to do. But don't get me started on everything. Although I'd love to talk about it. Please.
Thank you. If these computational contracts can be used to simulate likely outcomes, as you said, aren't we pushing the edge of predictive analytics? And isn't that a better way to do those simulations?
What would it mean? I mean, so given, if we say these are contracts about how the world will work, then we know a distribution of how the world actually does tend to work. Like
from history.
Yeah, from history, typically. Well, it might not just be history, because it might be that we know, it might be physics as well as history. It might be that we know we built a system, we built this mechanical system, we know the failure distribution for its parts, we can conclude what the failure distribution is for the whole system, those kinds of things. Or it might be pure history. It might be the temperature in Austin has been like this. But then we might have to add some physics, because we might say, but we have this global, increase in temperature, whatever it is, whatever might be happening or not happening. And then so it's a little complicated to know what the expected distribution of things in the world is. And by the way, it's there tend to be all these correlations about what happens in the world, and that's where it really matters to have sort of computable facts about the world. And this is where so lots of issues there. But maybe I didn't. What is
That's pretty close. But when we do predictive analytics, we put a lot of time into collecting the data first, and then doing the analytics, right? So in these computational contracts, it doesn't appear to shortcut that data collection period very much, does it?
No, it doesn't. What it does is it says, okay, like for example, let's take a very simple example, which people already do to some extent. When you have a pricing model, when you have pricing engines, right? Like we do this in our company. We have a complicated pricing engine that's essentially a computational contract about if you buy this number of copies in this different blah, 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 blah. Now we want to know, what is, if we make this tweak to this contract, how will that affect the expected revenue, right? And that's something that we get to do if we have it in computational form. If we say, you know, if it's in written form as legalese, and we say, gosh, if we change this clause, we say, what will happen? Who knows? You know, you have to write a whole program to do that. Yeah.
Thank you very much. What would be some of the mechanisms that you would advocate for making sure that whatever constitution we do write for these systems is more future-proof than the typical case? What would be an example mechanism for evolving a constitution?
That is a good question, and I have thought about that a bunch, and I don't have a really good answer. I mean, in other words, it's
so there's
like...
There's plenty of opportunity and work.
Yeah, yes.
There's plenty of work and opportunity.
Yeah, right. I mean, it's like saying, that question is like talking about, you know, the irresistible force and the immovable barrier. You quickly get into these things which are kind of paradoxical. You want it to change, but you don't want it to change.
Could you give it a lifespan?
What's that?
Could you perhaps give it a lifespan and we'll revisit it at a particular time?
Yeah, that's not an unreasonable thing, but then you know, I can imagine, let's see, how would that fail? Every one of these simple things has a nasty failure case. I think, I mean, that's not obviously silly, and that's something that human contracts tend to do. They tend to say this will be valid for 5 years or something. So that might be a good start. But I think, yeah, I mean, the one issue is, so if you know it's going to end at a certain time, there's probably a lot of gamification, you know, gaming that you can do just knowing that it's going to end. And so even knowing with certainty that there is an end I'm not sure, I can't figure that out right now, but I think that may have a nasty kind of way of cycling back into things that are happening even right now. But it's not a bad place to start.
Thank you.
Yeah.
So you've made some predictions, I guess, about the practical implications to humans of some of these new technologies. I'm willing to be willing to do that for quantum computing over maybe the 25-year time horizon. Can't think of anyone else I'd rather hear their thoughts on this.
Well, so, you know, it's funny because I worked on quantum computing back in the early 1980s with a physicist named Richard Feynman. And we basically concluded that we didn't think it was going to work. Okay? And the reasons we thought it wasn't going to work haven't actually changed that much. And, you know, the companies that have been trying to do it, you know, there's a lot of struggling you know, we've built frameworks that represent the quantum mechanics of what's going on, and we say, let's connect these to actual quantum computers. Well, I can say that so far we have never yet actually done that. I mean, within a minute we will know whether the thing is actually doing quantum stuff or not. But, you know, so it's been okay, so what do I think about it? The fact is the formalism of quantum mechanics is an elaborate formalism, and the trouble is that there are pieces of what has to happen in quantum computing that are outside of the core formalism of quantum mechanics. They mostly have to do with measuring the outcome from the quantum computation. And it's really not obvious that that works out okay. Because, you know, you can figure out everything inside the formalism. And by the way, the great advantage of quantum computing right now is that it has very nicely, you know, the formalism has really illuminated the formalism of quantum mechanics in a nice way. In fact, I can even say, you know, I spend my life designing Wolfram Language and functions for it and so on. And as a result of designing stuff for quantum computing, I invented a nice new functional programming construct recently that's relevant for ordinary computing. And that just came out of thinking about quantum computing. But in terms of, you know, do I think that, you know, we'll be able to factor large numbers with wild abandon on quantum computers anytime soon? My guess is no. My guess is that it may not work at all. I think that, you know, again, a topic not to get me started on is kind of going back into the fundamental theory of physics and whether the current formalism of quantum mechanics is actually right and whether it's the whole story, which I think it is not. But that's, you know, so I'm not that concerned about, you know, an overturning of what we currently think of in computing. I wrote, let's see, where was it? Last April 1st, I wrote this blog post about, I just was having fun writing about sort of the ultimate collection of buzzwords. The funny thing is well, there's a lot of interesting science to say about this, because it turns out that the notion of consensus in blockchains is bizarrely similar to the notion of measurement in quantum mechanics. That is, you know, what happens in quantum mechanics, things happen, and there's entanglement and so on, but then eventually you believe that a definite outcome occurred. And to get to that definite outcome, you kind of need to spread that little quantum effect among a whole bunch of nodes, you could say, and you need to do it in such a way that there's effectively irreversible behavior. And that's very similar to what happens in blockchains. Actually, neural nets have the same type of thing, that they are, they're making these attractors where you have kind of irreversible behavior. All these different pixel arrays all turn into, that's a tiger, that's an elephant, and so on. So it's kind of, to my amusement, so to speak, I mean, this started as kind of just a fun thing I was going to do for last April 1st, but actually it's quite a lot of interesting science and a lot of kind of interplay between the conceptual ideas in these different areas. Please. Yeah, we need to wrap up. Okay. All right. Do we have time for one more? Okay. Sorry, I'm having a chat.